Now, continuing in our understanding of electromagnetic radiation, we need to look at Einstein, who said that electromagnetic radiation can be viewed as a stream of particles, whereas electromagnetic radiation, we just talked about, is typically thought of as waves. Well, he called these particles photons, and using that same equation that we had above, could calculate the energy of a photon. He then went on to derive the equation that most people know him by, which is E equals mc squared. Energy has mass. And through this, you can calculate the apparent mass of a photon. And it's the apparent mass of the photon because it would be a different mass at each different frequency or wavelength, depending on which way you look at it, since they're related. It would have no mass if it was at rest. Depending on the frequency it was moving at, it would have a mass. Now, de Broglie said that particles exhibit wave-like properties, which goes directly along with Einstein because it's sort of the opposite. So he figured out that the mass is Planck's constant divided by the wavelength times the velocity. And that is V for velocity. I know it looks a lot like nu, but they're different. When we rearrange this to solve for the wavelength, so wavelength times m would equal h over v. So then the wavelength would be h divided by m and v. Let's see, here we would just multiply both sides by lambda, and then here we would divide both sides by m. This is called de Broglie's equation. So we can use this to calculate the wavelength of a proton. So wavelength is Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, divided by the mass. Whoa, don't want that. 1.6726 times 10 to minus 27. Not kilojoules, excuse me. Don't want to erase my fraction line. Kilograms. And times 10 to the 7th meters per second. Alright, so let's plug this all into the calculator. We have 6.626 times 10 to the minus 34. That is not right. There we go. Divided by 1.672 262 times 10 to the minus 27, also divided by 1 times 10 to the positive 7. And remember, you're dividing by everything that's on the bottom. So you get 3.96 times 10 to the minus 14. Okay, but what are the units on this? Okay, let's look at the units separately. We've got joules times seconds. And on the bottom, we've got kilograms, meters per second. It doesn't really look like anything cancels. So we need to know what joules are. Joules is kilogram meter squared per second squared. So let's plug that in. Kilogram meters squared per second squared times seconds is what we have on the top. And kilogram meters per second is what we have on the bottom. Well, dividing is the same as multiplying by the reciprocal. So, kilogram meters squared times seconds over seconds squared times seconds over kilograms and meters. So we've got seconds squared and we've got 2 seconds. We've got kilograms on the top and kilograms on the bottom. We have 1 meter on the bottom and 2 meters on the top. So we are left with the unit of meters, which makes sense since we're solving for a wavelength. Now, we can do this same calculation for something large like a ball as well. Now, diffraction is when light is scattered. Regular array of points or lines, sort of like when you have light scattered through a prism. We can have constructive interference, where the waves line up, and so they add together. We can have destructive interference, where they're opposite each other, and they subtract. Now, looking at the diffraction pattern of an electron beam that was diffracted by a crystal is what confirmed de Broglie's equation and confirmed that all matter exists of both particulate and wave properties.